Okay, so now we're going to finish out this practice problem set, starting with number 6. And number 6 is a question that I did not have any idea what they were going for when I first saw it. I think it's confusing, but now it's kind of a popular question. Here's what we've got. We've got a glass tube, and we've got cotton balls that have been soaked in solution stuck on either side. Over here on the left, there is an acid solution. Over here on the right, there is some kind of weak base solution. And these things both have a certain vapor pressure. And so gas particles are coming out of these cotton balls. Clearly, they would be coming out in this direction, but nobody cares. What we're looking at is they're coming out here in heading into the tube. When the two meet, a reaction will occur and a white solid will be formed. And so now the question is, where is that reaction going to occur? So this question is really about what are the relative molar masses of the two solutions. And so they want to know which one of these combinations will get us closest to the center of the tube. That means is we want gas particles that are going to move at roughly the same speed, so they meet in the middle. If we had a really heavy, slow gas, it would only come out a little ways, and a really fast, lighter gas for the other one, it would go really fast, and they wouldn't meet in the middle at all. They'd meet like somewhere over here. We want them to meet in the middle. We want them to have roughly the same molar mass. So you have to add up everyone's molar mass. When you do that, you will immediately rule out C and D because HBr is really heavy. And so you're down to A and B. For B, HCl is about 36.5 and ammonia is about 17. But if you go to A, HCl is about 36.75, and I think this methyl amine is going to be about 31. These are the two that have the closest molar mass. Taking a look at question 7, you read through it, there's all kind of stuff happening with volume and pressure and blah, 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 blah. And then the question is, what effect do the volume and pressure changes have on the average kinetic energy? So this is a trick question. What effect does anything have on average kinetic energy other than temperature? And the answer is nothing. None of these things are going to change the temperature. My guess is if you dig around in here, here it is, temperature is held constant. So temperature being held constant, the average kinetic energies are the same. Average kinetic energy stays the same. One, it doesn't increase, it doesn't decrease when you change the pressure and volume. And it's not that it can't be determined, it can. We know it stays the same. Taking a look at number 8, okay, so when they do this, they are using these arrows to represent the relative speeds of the particles. So if you look at diagram 1, all the arrows are the same length. If you look at diagram 2, you got some really short ones, you got some really long ones. So the long arrows represent faster moving particles, and the shorter arrows mean they're moving slower. So which of these diagrams best represents the speed of the particles at a fixed temperature? You're always going to have a distribution of speeds. That's why these curves are like this. You know, they're not just a single peak. They don't just go up and down, and everybody's moving at this one temperature. They have a range and a broad range that meets at an average. So diagram 1 is out. It's diagram 2. Let's look at why. C says because the particles have a net kinetic energy of 0. Well, that would be absolute 0, so that's not happening. D, here's the correct answer. Diagram 2, because they have a variety of different speeds. And then finally, question 9, half a mole sample of helium and half a mole sample of neon placed in 2 10-liter rigid containers at 25 degrees C. Each has a pinhole. Okay. So this is one of those a fusion through a pinhole questions you see a lot. And the idea here is heavy guys move slower, lighter guys move faster. By moving faster, the lighter guys are positioning themselves to more frequently hit the sidewalls and more frequently find that little opening they're going to get out. So, we know that the helium will escape faster. Helium will escape faster because the atoms are moving at a higher average speed than the neon atoms. That's it. And you'll notice here, they've kind of figured out my, oh, look, if you don't know what you're doing, look for the two that are kind of the same. In this case, the two that are the same are both wrong answers. That strategy only works if you're lost. If you're not lost, and you shouldn't be lost here, because it's pretty easy to know that the light guides move faster, and they're going to find the hole more often. So there you go. That's it. Bye-bye. Oop, Quince.